Good day everyone, my name is Kanyisa Sowazi and welcome to my YouTube channel. Today we're going to be discussing about the application of calculus in our real lives. So I'm going to start off with the introduction into the topics and then further discuss the subtopics that are covered in calculus. And then I'm going to walk you through some real life examples of how it is applied and give a detailed explanation of how it is applied in these real life situations. So without wasting any time, let's get on with it. Modern calculus was developed in the 17th century by Isaac Newton and Gottfried Leibniz. Newton used calculus to explain the force of gravity and the motion of planets around the Sun. Even though Newton and Leibniz are credited with creating calculus, there has been a lot of contributions from many great minds into the topic. Calculus is a mathematical study of continuous change. You might be asking yourself, what do we really mean about this? Well, let's take a look at this example to make things a little bit more clearer. Let us look at an example with point A and point B in space. Now let's assume that the distance between point A and point B is 100 meters. Let's assume for argument's sake that point A is our home and point B is a shop where we usually go and buy milk. And let's say the distance from home to the shop is 100 meters. We will assume in this example that it takes us about 1 minute to get from home to the shop and 1 minute to come back. And therefore, our velocity is 100 meters divided by 1 minute, or 100 meter per minute. Maybe now would be the best time to explain the difference between velocity and speed. Velocity is the displacement from A to B over time taken to get from A to B, while speed is the actual path traveled from A to B over the time taken to get there. Therefore, speed accounts for the total path that is traveled. That is, if going to the shop, you'd have to take a turn, maybe a turn left and then a turn right. You will have to include the whole distance that you took to get there. Whereas the velocity would only require you to consider only the movement from A to B and therefore just take the straight line of the points. This means that speed is always greater than or equal to the velocity. But in our example, we are going to assume that speed and velocity are the same, meaning that we are going on a straight path. And now let's make another assumption. Say for some reason while going to the shop, we took our time going slowly to the shop because we maybe were lazy to go there. And then on our way back, when we checked our time, we realized actually our favorite show is gonna play, and then we started going faster. And now we wanted to measure the velocity that we took for the last 10 meters going home. Now obviously the velocity going home on the last 10 meters will be way higher than our average velocity because of our acceleration towards the end. And now if we shorten the length even smaller and smaller and say we want to take the last 1 meter going home, now that will probably even be more faster than average velocity. And now if we dissect that even further and further and further up to one singular point and then measure the instantaneous velocity at that single point, at that point it is difficult to measure, as for our average velocity it's just a simple mathematics, right? We just take the length that's taken to get from A to B, which is our 100 meters, and then divide by the time we took to get there. But the smaller and smaller our distances become, the harder it becomes to measure our velocity. So that is where calculus is applicable. Calculus concerns itself with those instantaneous rates of change or instantaneous velocities. Now I hope that this previous example made things a little bit more clearer now. Now moving forward, calculus is divided into two main branches, which is differential and integral calculus. Differential calculus concerns itself with the instantaneous rates of change and slopes of curves, while integral calculus concerns with the accumulations of these small changes and also areas under curves. Now, differential and integral calculus are related to each other by the fundamental theorem of calculus. What this theory states is that if you take a function, differentiate the function, and then integrate it again, you'll get back the original function that you differentiated in the first place. Calculus has a lot of application in physics and engineering, which are a bit obvious, but also has seen a lot of application in actuarial science, computer science, statistics, economics, business, and any field that you can think of. When in all fields, it's almost certain that you're going to have problems that you need to solve. And if there are possibilities of solutions, there's always an optimal solution that you can find, which is where calculus enters. In our first example application of calculus, we are going to start off with the problem of population growth rates. Now, population growth rates has a lot of application in many different fields. It can be used in actuarial science to predict the population growth and death rates for life insurers. This becomes very important, especially in the pricing of policies to determine the premiums to be paid by clients. It is also important in microbiology in testing the growth rates of bacteria in different environments as part of research. It is also used in medicine to determine the growth rates of viruses during treatment, to test whether the virus is responding to the treatments that have been found. It might also be used by governments to determine the future demands for resources so that the government can better prepare their resources more effectively. On further with our example, let's assume that we have a universe, and in our universe we have a sphere. Now, we only have one sphere at time equals to 0. Now assume that time passes by, and then we have 2 spheres in our universe. And then another time passes by, and then we have 4 spheres. And another time passes, and then we have 8 spheres. Now, if we look at the distribution of our spheres in our universe with respect to time, you'll realize that it forms an exponential function. From this example, we can deduce that the growth rate of our population is directly proportional to the current population multiplied by some constant, of which in our case, our constant is a 2. Now, we use this constant as a multiple of our population, which really defines the population growth rate at any given time of the. For simplicity, I have replaced our population with capital letter P and replaced our time with small letter t. As you can see, this is a table of our first 3 iterations of our population growth model. Therefore, now our current growth model depicts that a rate of change of population, which is dp by dt, is equal to our constant k times the current population at time equals to t. Now we can try and simplify our formula by introducing a number dt over p, of which on the left hand side our dt's will cancel and we will be left with dp over p. And on the right hand side, our p's for population will cancel and we'll be left with k times dt. The final equation that we are left with is what is known in calculus as a separable differential equation, which is dp over p equals to k times dt, meaning that on the left hand side we have our variable p, and on the right hand side we have our variable time, and therefore we can solve these separately. Now we can insert an integral on both sides. The integral of 1 over p times dp is equal to the natural log of p, and the integral of dt is equal to t plus some constant on the side. If we introduce Euler's constant E on both sides, on the left hand side we are left with P, which is our population, and on the right hand side we are left with e raised to k times t plus c. And if we simplify this, we are left with e raised to k times t times e raised to c. But e raised to c is a constant, of which we can name it a. And therefore we are left with the final equation of population p equals to a times e raised to k times t, which is our population formula. From this formula, we can get our population at any time. Because of time, I'm gonna stop this video at one example. I hope that this was very helpful and it helped you really see the applications of calculus and all the possibilities that it has. Now thank you all for watching this video. As always, if you like the video, please hit the like button, and if you'd like to see more videos similar to this one, please don't forget to subscribe. Thank you. Till next time. Bye.